Welcome to lecture 29. We are talking about high vacuum measurement. So, today we will be talking about Knudsen gauge. We have talked about McLeod gauge, we have talked about ionization gauge, we have talked about thermal conductivity gauge. We will now start our discussion today with Knudsen gauge. Then we will also talk about briefly molecular momentum gauge and solid state pressure sensor. Now, what you see is a schematic of a Knudsen gauge. Consider a chamber to which we will admit the fluid pressure which I am going to measure. Inside the chamber, I have two fixed plates. This is one plate, this is another plate. So, I have two fixed plates mounted within a chamber, and in between these two fixed plates there is a spring restrained movable vane. So, you have a spring restricted movable vane in between two fixed plates. So, the movable vane can show some angular motion between these two fixed plates. Now, these two fixed plates are heated up to an exactly known temperature. And the movable vane's temperature is different from this. The temperature of the movable vane is lower than the temperature of the two fixed plates. Now, you apply vacuum, that means you connect this chamber to the vacuum source. So, the gas is admitted to the chamber. Now, gas near the hot plate will have a higher temperature than the gas near the colder vane, because I have heated up these two fixed plates. So, two fixed plates temperature is higher than the temperature of the movable vane. Let us consider the movable vane's temperature is same as the temperature of the gas. So, when the gas molecules rebound from the heated plates, they will rebound with greater momentum than from the cooler movable vane, because the gas near the hot plate has a higher temperature than the gas near the colder vane. So, what will happen is a net momentum will make the assembly rotate. That means, the net momentum on the movable vane will make the movable vane rotate. Now, this rotation can be considered as a measure of the pressure or vacuum. So, how do I measure this angular rotation of the movable vane? For that, please note that there is a mirror attached on the movable vane. So, I send a beam of light to the mirror, and here I have put a scale and a spot of light is reflected from the mirror. So, as the movable vane rotates, this rotation can be amplified by this optical arrangement. So, small rotation by the movable vane will cause a larger displacement of this spot of light on this scale. So, by looking at the displacement of the spot of light on the scale, I can measure the angular rotation of the movable vane, which is a measure of the vacuum or the low pressure. So, let me explain one more time. I have a chamber which is sealed and connected to the vacuum source which I am going to measure. Within this chamber, I have two fixed plates mounted. These two fixed plates are heated up at an exactly known temperature. The temperature of the movable vane is lower than the temperature of the fixed plates, and the temperature of the fixed plate as well as the temperature of the movable vane are exactly known. So, two fixed plates have same temperature, let us say T f, and the movable vane has temperature, let us say call it T v. So, T f is greater than T v. Now, the gas molecules will be colliding randomly with the fixed plates as well as with the movable vane. Fixed plates has higher temperature than the movable vane. So, when the gas particles rebound from the hotter plates, they will come back with a greater momentum than compared to the case when it rebounds from the colder vane. So, this will impart a net momentum which will cause the movable vane to rotate by some extent. This angular rotation is a measure of the pressure. This angular rotation can be amplified by an optical lever arrangement. So, what we do is we send a beam of light and there is a mirror attached on the movable vane. So, a beam of light is sent to the mirror and a spot of light gets reflected from the mirror and falls on the scale that is attached. So, a small angular rotation will cause a large displacement of the spot of light on the scale. So, by measuring this displacement, I can measure the pressure. So, there is a formula available for this. This formula was derived by Knudsen himself. So, gas molecules rebound from the heated plates with greater momentum than from the cooler movable vane. This gives the net force on the spring restricted movable vane. The force can be measured by the deflection of the movable vane. The gap between the fixed plates and the movable vane must be less than mean free path of the gas molecules. This is very important. So, the gap between the two fixed plates and the movable vane must be very small, and this should be smaller or less than the mean free path of the gas molecules. Because of this condition, we cannot use this instrument for measurement of higher pressure, because the condition that the gap between the fixed plates will be smaller than the mean free path of the gas molecules can be met only at very low pressures, because at low pressures the mean free path of the gas molecules will be larger compared to the case when I am talking about higher pressures. So, the relevant dimensions of the gauge is less than the mean free path of the gas molecules. So, if this is the case, that we have two fixed plates temperature T f and we have movable bench temperature as T v and T f is greater than T v, then the pressure or the vacuum can be computed using this formula. P, which is pressure, is equal to K times F divided by square root of T f minus T v minus 1, where small p is gas pressure, capital F is force and K is a constant for the Knudsen gauge. T f is the temperature of the fixed plates and T v is the temperature of the movable vane. Note that the fixed plates can be heated up by an electric arrangement. So, you can install a heater to heat up the fixed plates and we must measure the temperature of the fixed plate and the movable vane exactly. This formula, which can be used to measure the vacuum from known temperature of fixed plates and movable vane and the force, was derived by Knudsen. This formula was derived by Knudsen with the assumption that the distance between the fixed plates and the movable vane is less than the mean free path of the gas molecules. So, above 10 to the power minus 3 torr, this condition is generally violated. So, we cannot measure a pressure which is higher than 10 to the power minus 3 torr. Remember that 1 torr is 1 millimeter of mercury. So, typical range of the Knudsen gauge is 10 to the power minus 8 torr to 10 to the power minus 3 torr. Certain important points about Knudsen gauge. It is an absolute gauge in the range of 10 to the power minus 8 to 10 to the power minus 3 torr. It is independent of gas composition. Please note that in the formula that will be used for measurement of pressure or computation of pressure, no information about the gas that is being used has been put. So, the pressure measurement is independent of gas composition. This is mostly suitable for laboratories. It is generally not used in industry. It depends on momentum transfer principle and Knudsen gauge in the range it is used like 10 to the power minus 8 to 10 to the minus 3 torr can also be used as a standard for calibration for other pressure measuring instrument in this particular range, that is 10 to the power minus 8 to 10 to the power minus 3 torr. Now, let us talk about another vacuum gauge known as molecular momentum gauge. A molecular momentum gauge have two basic working parts, a rotating cylinder and a restraint cylinder. The gas molecules from the vacuum chamber comes in contact with the rotating cylinder at a constant speed of 3600 rpm. Thus, they acquire energy, experience a momentum change and are set in motion in the direction of rotation. When these molecules strike the restraint cylinder, they transfer energy to it. Such molecular collisions move the restraint cylinder and the displacement is proportional to the energy transferred. Energy transferred is a function of the number of gas molecules present in the chamber. The number of molecules per unit volume is related to the absolute pressure of the gas. Thus, the pointer attached to the restraint cylinder indicates the gas pressure on the scale. So, in a way it has some similarity to the Knudsen gauge. Both works on momentum transfer. So, let me go through once again the working principle of molecular momentum gauge. A molecular momentum gauge have two basic working parts, a rotating cylinder and a restraint cylinder. The gas molecules from the vacuum chamber come in contact with the rotating cylinder at a constant speed of 3600 rpm. Thus, they acquire energy, experience a momentum change and are set in motion in the direction of rotation. When these molecules strike the restraint cylinder, they transfer energy to it. Such molecular collisions move the restraint cylinder and the displacement is proportional to the energy transferred. Energy transferred is a function of the number of gas molecules present in the chamber. The number of molecules per unit volume is related to the absolute pressure of the gas. Thus, the pointer attached to the restraint cylinder indicates the gas pressure on the scale. Capacitance type pressure sensor. This consists of thin diaphragms and can measure pressure down to 10 to the power minus 5 torr. So, it consists of a tensioned diaphragm. The material used for making the diaphragm are Monel, Inconel, ceramics, etc. Note that you have electrodes here and this is the thin diaphragm, thin tensioned diaphragm. This part, let us say we keep under high vacuum. Now, when we apply pressure, that means when this connected to the vacuum source, you will have the gap changed. So, you will get an electrical signal as output. So, this way a capacitance type pressure sensor can measure low pressure up to 10 to the power minus 5 torr. Next, let us talk about a solid state pressure sensor. Solid state pressure sensor is based on integrated circuit technology. Finds extensive application in the range of 0 to 100 kilopascal. The basic sensing element is small wafer of silicon that acts as a diaphragm. The deflection of the wafer is sensed by a strain gauge grown directly on the silicon wafer. Even signal conditioning circuitry for say temperature compensation and linear pressure voltage output is also grown directly on the wafer. So, the solid state pressure sensor is based on integrated circuit technology. it is a new generation pressure sensor. So, the basic sensing element is nothing but a thin wafer of silicon that acts as a diaphragm. So, diaphragm is the basic sensing element, and the diaphragm is made of a small wafer of silicon. Now, if pressure is applied to the diaphragm, you know the diaphragm will deflect. Just now we have seen the capacitance type pressure sensor. So, this deflection of the diaphragm is a measure of the pressure. So, how do I measure the deflection of pressure? One way to do that is to use a strain gauge. We have talked about strain gauge when we talked about transducer elements. So, now what we can do is we can grow a strain gauge directly on the silicon wafer. So, when the silicon wafer undergoes deflection, the strain gauge also undergoes strain. So, it changes its resistance and an electrical signal will come out as output, which is a measure of the strain, which in turn is a measure of the deflection, which in turn is a measure of the pressure. In fact, what we can also do is we can grow the signal condition circuitry directly on the wafer. So, such signal conditioning circuits will be helpful for nullifying the effect of ambient temperature, that means for temperature compensation as well as for making pressure voltage output linear. So, the solid state pressure sensors are very advantageous because they have these distinct features. It is based on an integrated circuit technology and just consists of a small wafer of silicon, where you can grow the strain gauge or the signal conditioning circuits all together. So, this can measure gauge pressure, absolute pressure as well as differential pressure. So, this is the silicon wafer which acts as a diaphragm. So, see, this is one pressure source, this is another pressure source, this may be atmospheric pressure, and then this is gauge pressure is being measured. Now, if you look at closely this silicon wafer, we have this. So, it is a silicon wafer where we have the strain gauge and the other signal conditioning circuits all grown on the silicon wafer. So, this is electrical connections to wafer. So, as we apply pressure P 1 from here, you apply pressure P 2 from here, the wafer undergoes deflection because of these differences of these two pressure. This deflection is sensed by the strain gauge grown on the wafer and corresponding electrical output is noted. If this pressure is atmospheric pressure, we are measuring gauge pressure. If this is sealed and completely evacuated, we are measuring absolute pressure. So, you can measure gauge pressure, absolute pressure, differential pressure. For differential pressure, these two pressures are different. So, it is a very simple arrangement and very useful in the measurement of pressures in the range of 0 to 100 kilopascals. The main advantage is it gives you an electrical output, simple in functioning, and you can grow the strain gauge as well as the electric signal conditioning electric circuits all on the diaphragm or silicon wafer itself. So, certain important characteristics of solid state pressure sensor. It has very high sensitivity, 10 to 100 millivolt per kilopascal, high accuracy and reliability, fast response time is on the order of 10 milliseconds, linear voltage versus pressure within the specified operating range, temperature compensation for broad range of temperature 0 degree Celsius to 60 degree Celsius, temperature compensation is available. It is easy to use, often with only 3 connections: DC power supply about 5 volt, ground and the sensor output voltage. So, these important characteristics made solid state pressure sensor a very useful pressure measuring instrument in the range of 0 to 100 kilopascals. It has high sensitivity, high accuracy, high reliability, and above all it is very simple to use, gives you electrical output. So, we will stop our discussion